And now in this lecture we find out the value of the shaded area. In the drawing we have a circle inside a quarter circle. We know that the radius of this circle is equal to the square root of 2 units. And our mission is to find out the value of this shaded area. Okay, so first of all we define the relevant points to this question. So we define this point as A, we define this point as B, we define the center of the quarter circle, this point as O, we define this point as C, we define this point as D, we define the touching point between the small circle and the big quarter circle as E, and finally we define the center of this small circle, this point, as F. In the next step we join points F and C together by a straight line. Point F is the center of this small circle, point C is the point of the small circle itself, therefore FC is the radius of this circle, is equal to the square root of 2 units in its length according to what is given as the question. We can implement in this drawing rule 1, I repeat quickly on rule 1, according to rule 1. A tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have tangent AB that is tangent to this circle, this point M. Point M is the point of tendency. And we have also the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule 1. So we can actually implement rule 1 in our drawing. Because in our drawing we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. So if OD is perpendicular to CF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, FB is the radius of this circle. The radius FB is drawn to point B, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius BC. If DA is perpendicular to BC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the rule 1. In the next step we'll focus on this small quadrilateral BFOC. Inside this small quadrilateral BFOC we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of this fourth angle. In total the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this small quadrilateral BFOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So inside quadrilateral BFOC we have 4 right angles. Any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral BFOC is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF equals to the opposite side OC in rectangle BF OC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side FC must be equal to the opposite side BO. But FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So I actually found out that quadrilateral BFOC is not a rectangle but a square, because all of its sides are equal to each other, each side equals to the square root of 2 units in its length. In the next step, we join points O and F together by straight line. By joining points O and F, we created the right and associated triangle OBF. In the right and associated triangle OBF, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So inside the right and associated triangle OBF, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle OBF? We have this angle. This is equal to 90 degrees. It is a right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha. In total, they must be equal to 180 degrees. According to the rule dimension. So in the right triangle OBF, 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation. And finally we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2. And finally we get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So here this is angle alpha is equal to 45 degrees in its size. And this is also angle alpha is equal to 45 degrees in its size. In the next step, we'll implement the Pythagoras theorem on this right and associated triangle OCF. According to the Pythagoras theorem, in the right triangle OCF, the right triangle OCF, the square of the hypotenuse must be equal to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle OCF is OF, therefore the square of the hypotenuse is OF squared. It must be equal to FC squared plus OC squared. Repeat again. In the right triangle OCF, according to the Pythagoras theorem, OF squared equals to FC squared plus OC squared. So OF squared, that is the square of the hypotenuse, equals to FC squared. FC is square root of 2, therefore FC squared is square root of 2 squared, that is 2, plus OC squared. OC is also square root of 2, therefore OC squared is square root of 2 squared, that is 2. So So if we're going forward that OF square equals to 2 plus 2, that is 4. Here we take a root out of this equation, and finally we get that OF equals to the square root of 4, that is 2. So here the length of the hypotenuse OF, it is actually equals to 2 units in its length. Write it down. So here, point O is the center of this quarter circle, and point F is the center of this small circle. The hypotenuse OF actually it connects the two centers together. And we have here rule number 9 that we can implement in our drawing. According to rule 9, according to rule 9, whenever you have an internal line between two circles, like in this drawing, the two circles touching each other internally at point P. Point P is the touching point or the point of tendency. So according to this rule 9, the center of this big circle is here at point O, the center of this small circle is here at point M. And the straight line that connects the centers together is the straight line OM. And according to this rule 9, the straight line OM must pass for their touching point, that is actually point P. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. We can implement rule 9 in our drawing. Well, because in our drawing, we have the straight line OF that connects the center of those two circles together. And according to rule 9, the straight line OF must pass for their touching point, that is actually point E. Or OFE is one straight line. Here OFE is one straight line. OFE is one straight line. If OFE is one straight line, it means that OE is also one straight line. OE is one straight line. Point O is the center of the quarter circle. Point E is the point of the quarter circle itself. This is exactly the definition of a radius. So OE is the radius of the quarter circle. We define the radius of the quarter circle as capital R. Therefore, OE equals to capital R. That is the radius of the quarter circle. OE equals to capital R. And OFE is one straight line. We define the intersection point between line segment OF and this small circle as H. And focus on edge FE. If OFE is one straight line, it means that edge FE that is part of OFE must be also a straight line. So we have the straight line edge E that touches the circle at point H and E. Any straight line that touches the circle at 2 points is defined as a chord. So edge E is a chord. Is a chord inside the small circle. And chord edge E passes for point F, that is the center of this small circle, and we know that any chord that passes for the center of a circle must be the diameter of the circle. Therefore, edge E is the diameter of the circle. I write it down. Edge E is the diameter of the small circle. Edge is the diameter of the small circle, and we know that any diameter of any circle bisects the circle into two halves. So edge E, the diameter edge E, bisects the circle into two halves. The first half is this is the first half. So So this is actually a semicircle, and this is the second half. That is also a semicircle. You can say that this is a semicircle, and what is actually the area, the value of the shaded area? The value of the shaded area in total, it will be equal to the area of sector AOE, this sector AOE. The value of the shaded area is the area of sector AOE, this sector AOE of the quarter circle or the big circle, minus the area of this semicircle, minus the area of the small semicircle, minus the area of this small shape that is actually shape HBO, minus the area of the orange shape HBO. Repeat again. The value of the shaded area equals to the area of sector AOE minus the area of the semicircle minus the area of the orange shape HBO. It is very easy to see from the drawing that the value of this shaded area equals to the area of sector AOE minus the area of this semicircle minus the area of this orange shape. This is the area of this shape ABAE. Okay, so we'll find out each of the areas and then subtract them, and this way we get the value of this shaded area. So first of all we have to find out the area of this sector AOE. What is the area of sector AOE? Here, this is how write down the area of a sector. Here, this sign above AOE is the sign for a sector. It means the area of sector AOE. What is the area of a sector? The green shape is sector AOB. This is sector AOB, the green color. Sector AOE is like a slice of a cake. If the circle is a cake, then a slice of a cake is a sector. Okay. The two legs of this sector AOB are AO and OB. They are both the area of the circle that is equal to R. So what is the area of this sector AOB in the green color? The area of the sector AOB equals to the area of the circle that is pi r squared times theta over 360 degrees theta. This is angle theta. This is actually the angle between the two legs of this sector. The first leg is AO and the second leg is OB. Okay, repeat again, the area of this sector AOB equals to pi r squared times theta over 360 degrees. We can use this new formula in order to find out the area of this sector AOE. So the area of sector AOE will be equal to pi times capital R squared, that is the area of the big circle. Pi times capital R squared, the area of the big circle, times theta over 360 degrees. Theta is the angle between the legs of this sector AOE. The angle between the legs of sector AOE, this angle is 45 degrees. So it is 45 degrees over 360 degrees. So it is pi, and we already found out that capital R, the radius of the big circle, what is the radius of the big circle? Actually, we have to find out the radius of the big circle here. We already found out that OE equals to capital R. That is actually the radius of the big circle. We know that point F is the center of this small circle, point E is the point of the small circle itself. For FE is the radius of the small circle. This equals to the square root of 2 units according to what is given as the question. We have already found out that OF, the hypotenuse OF, it is equals to 2 units in its length. So the radius, capital R, equals to OE, and OE equals to OF plus FE. So OF is 2 plus OE is square root of 2. So in conclusion, we found out that the radius capital R of this quarter circle equals to 2 plus square root of 2. Okay. R equals to, capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that R square equals to 2 plus square root of 2 square times 45 degrees over 360 degrees, it is 1 over 8. So we have to divide it by 8. So here we have pi, inside the brackets we have 2 plus square root of 2 square. 2 plus square root of 2 square equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2 divided by 8. So it is pi, inside the brackets we have 4 plus 2, that is 6, and 2 times 2 is 4, so in total this expression equals to 4 times square root of 2 over 8. Here we'll divide both the numerator and the denominator of this expression by 2, and we get here is equals to pi, and we have inside the brackets in the numerator 6, so 6 over 2 is 3, plus we have also 4 times square root of 2. 4 over 2 is 2, so in total in the numerator we will have here 2 times square root of 2 over 8. And we have to divide also the denominator 8 by 2. 8 over 2 is 4. So in conclusion, found out that the area of sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4. Repeat again. The area of this sector AOE, is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we'll find out the area of this semicircle. The small semicircle. The area of any semicircle equals to the area of the circle, that is pi r squared over 2. So it is pi and r is square root of 2. If r is square root of 2, it means that r squared is square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1. So this expression in total equals to pi. So actually we found out that the area of the small semicircle is equals to pi square units. The only thing that is left to find, in order to find out the area of this shape ABE, is to find out the area of this orange small shape. What is the area of the orange small shape? That is actually shape BHO. The area of the small shape BHO, it will be equal to the area of the right in the isosceles triangle BFO minus the area of this small sector BFH. Repeat again. The area of the orange shape BHO the area of the orange shape BHO equals to the area of the right in the isosceles triangle BFO minus the area of the small sector BFH. So actually the area of the orange shape BHO will be equal to the area of triangle BFO. Triangle BFO is an isosceles triangle and also a right triangle. The area of any triangle equals to the base of the triangle times the height to the base over 2. The base is square root of 2 and the height to the base is also square root of 2 divided by 2. Why? Because it's an isosceles triangle. So square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, we found out that the area of the right and the isosceles triangle BFO is 1 square units minus the area of the small sector BHF. What is the area of the small sector BHF? The area of any sector is pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is actually 45 degrees, as you can see here. 45 degrees over 360 degrees. The radius of the small circle equals to square root of 2 units in its length. So it is pi and r is square root of 2. If r is square root of 2, it means that r squared is square root of 2 squared, that is 2. And 45 degrees over 360 degrees, it is 1 over 8. So it is 2 pi over 8. Here we divide both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, over 8 over 2 is 4. So if we're going to find out the area of this small sector BHF equals to pi over 4. And in total, the area of the orange shape, the orange small shape, BHO is equals to 1 minus pi over 4 square units. So the area, the value of the shaded area in total is equals to the area of sector AOE and we have already found out that the area of sector AOE equals to pi times 3 plus 2 times root of 2 over 4. The area of sector AOE is pi times 3 plus 2 times root of 2 over 4 minus the area of the semicircle, and we have already found out that the area of the semicircle equals to pi square units, so it is minus pi minus the area of the orange small shape, and we already found out that the area of the orange small shape BHO is equals to 1 minus pi over 4. Repeat again. The value of the shaded area in total is equals to the area of sector AOE, that is pi times 3 plus 2 times root of 2 over 4 square units, minus the area of the small semicircle, that is pi square units, minus the area of the orange shape BHO, that is 1 minus pi over 4 square units. So here we'll open the brackets and we get that the area, the value of the shaded area ABE is equals to pi times 3 plus 2 times root of 2 over 4 minus pi. Here we'll open the brackets and get here minus 1, and minus times minus is plus, so it is plus pi over 4. Okay. So the value of the shaded area equals to, here we'll open the brackets, pi times 3 is 3 pi, plus 2 times root of 2 times pi is 2 times root of 2 times pi. Here we have minus pi plus pi over 4 is minus 3/4 of pi, and we have minus 1. So here we multiply minus 1 by 4 and then we divide it by 4 in order to have a common factor of the other two expressions. The other two expressions have denominator of 4, and you get that now the value of the shaded area equals to 3 pi plus 2 times root of 2 times pi minus 3 pi. Here we multiply minus 1 by 4, then we divide it by 4, so minus 1 times 4 is minus 4, divided by 4. So here we have 3 pi minus 3 pi is 0, so those two expressions will get cancelled. And we have here so the value of the shaded area equals to 2 times square root of 2 pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2. 2 over 2 is 1, so this expression total equals to, after we divide by 2, it equals to the square root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator of 4 also by 2, so 4 over 2 is 2. So in conclusion, we found out that the value of the shaded area is equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. And that is the answer to the question. I'll repeat again. The value of this shaded area equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. Okay, so in the next step, I will summarize the lecture. In this lecture, I found out the value of this shaded area. In the drawing, we have a circle that is inside this quarter circle. We also know that the radius of this small circle, r, equals to the square root of 2 units in its length. Again, our mission is to find out the value of the shaded area. Okay, so first of all, actually define names, define the point or give names to the points that is relevant to this question. We define this point as A, we define this point as B, we define the center of this quarter circle, this point as O, we define this point as C, we define this point as C, and we define the touching point between this circle to this semicircle, to this quarter circle as E, and finally we define the center of this small circle, this point as F. Then we join point F and C together by side line. Point F is the center of the circle, point C is the point on the circle itself, therefore FC is the radius of this circle, is equals to the square root of 2 units in its length. Okay. Then we implemented here rule 1. First of all, point F is the center of this circle, of this small circle. Point C is the point of this small circle itself. Therefore, FC is the radius of this circle. This is equal to the square root of 2 units according to what is given as the question. We can implement here rule 1. Why? Because we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OC will be perpendicular to the radius CF. If OC is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. FB is the radius of this circle, that is equal to the square root of 2. The radius of B is drawn to point B, that is the point of tendency of tangent AO with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle was 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral BFCO, we have 1, 2 flat angles. The sum of flat angles is 270 degrees plus the fourth angle. In total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle must be equal to 90 degrees. So inside quadrilateral BFOC we have 4 angles, and any quadrilateral that has 4 angles must be at least a rectangle, if not a square. So we relate to this quadrilateral BFOC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF equals to the opposite side OC. But BF equals to the square root of 2 units, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the sum rule, side CF must be equal to the opposite side BO in rectangle BFOC. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So actually found out that quadrilateral BFOC is not a rectangle, but a square, why? Because all of its sides are equal to each other. Then we join points O and F together by straight line. By joining points O and F, we created the right and associated triangle OBF. This right and associated triangle OBF, we implemented the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OF. Therefore, the square of the hypotenuse is OF square, so OF square must be equal to BF square plus OB square. Repeat again. According to the Pythagoras theorem, in the right in the associated triangle OBF, in the right in associated triangle OBF, OF square equals to BF square plus BO square. So OF square, that is the square of the hypotenuse, equals to BF square. BF is square root of 2, therefore BF square is square root of 2 square, that is 2, plus BO square. BO is square root of 2, therefore BO square is square root of 2 square, that is 2. So in conclusion, we found out that OF square equals to 2 plus 2, that is 4. Then we took out of this equation and finally found out that OF equals to the square root of 4, that is 2. So therefore OF is equals to the square root of 2 units. And in this right triangle OBF, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle OBF? We have this angle that is equal to 90 degrees plus alpha plus alpha. So in the right triangle OBF, 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtracted 90 degrees from the equation and finally found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. Here we divided the equation by 2 and finally found out that the missing angle alpha equals to 45 degrees in its size. Here this is angle alpha is equal to 45 degrees in its size, and this is also angle alpha that is equal to 45 degrees in its size. And we have already found out that the length of the hypotenuse OF is 2 units. Okay, then what is the value of the shaded area? The value of the shaded area, this area, equals to the area of sector AOE minus the area of the semicircle minus the area of this orange shape. Okay, repeat again. The value of the shaded area equals to the area of sector AOE, the big sector AOE, minus the area of the small semicircle, this small semicircle, minus the area of this orange shape BHO. So what is the area of sector AOE? We have the green shape AOB, sector AOB. Sector AOB has two legs, AO and OB, are both the area of the circle is equal to R. So the area and the angle between the two legs AO and OB is theta. So the area of this sector AOB equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Okay, so we can actually implement the new rule in order to find out the area of sector AOE. The area of sector AOE equals to, actually define the radius of the big circle is capital R. If this point it is the center of this small circle, point F. Point E is the point on the small circle itself, so for FE is the radius of the small circle is equals to the square root of 2 units according to what is given as the question. We have already found out that FO equals to 2 and OE equals to OF plus FE. OE is the radius of this big circle is equal to capital R. So R equals to OE equals to OF plus FE. OF is 2 and FE is square root of 2. So in conclusion, found out that capital R equals to 2 plus square root of 2. Therefore, if R equals to 2 plus square root of 2, it means that R squared equals to 2 plus square root of 2 squared. So the area of sector AOE equals to pi R squared times the angle between the legs of sector AOE, that is 45 degrees over 360 degrees. 45 degrees over 360 degrees. So it is pi and R is 2 plus square root of 2, therefore R squared is 2 plus 2 squared, and 45 degrees over 360 degrees is 1 over 8, so it is, we have to divide it by 8. And we have here, so the area of sector AOE equals to pi, and 2 plus 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2, divided by 8. 4 plus 2 is 6, and 2 times 2 is 4, so in total this expression equals to, in the numerator we have 4 times square root of 2 over 8. Here we divided both the numerator and the denominator of this expression by 2. So in the numerator we have pi, and inside the bracket we have 6, and 6 over 2 is 3, and 4 times square root of 2 over 2 is 2 times square root of 2 over 8, and we have to divide the denominator also by 2, and 8 over 2 is 4. So if we already found out that the area of sector AO equals to pi, and inside the bracket we have 3 plus 2 times square root of 2 over 4. Okay. So here we have rule 9 that we can implement. According to rule 9, in the drawing we have those two circles that are touching each other internally at point P. The center of the big circle is 0 at point O, the center of the small circle is 0 at point M. The straight line that connects the centers together is the straight line OM. So the straight line OM, according to this rule 9, must pass for the attaching point is actually point P, or OMP is one straight line. So OMP is one straight line. We can implement rule 9 in our drawing. Why? Because in our drawing we have point F is the center of this small circle, point O is the center of the quarter circle. So FO or OF is the straight line that connects the centers together, and according to rule 9, because we have here internal notch between the circle and the quarter circle, that is to say they are touching each other internally here at point E, can implement here rule 9. According to rule 9, the straight line OF that connects the centers together must pass for point E, that is their touching point. OF is one straight line. If OF is one straight line, it means that OFE is also the radius of the quarter circle. Why? Because point O is the center of the quarter circle and point E is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of the quarter circle that we define as capital R. So if capital R equals to OE, it means that capital R, that is the radius of the quarter circle, must be equal to OF plus FE. OF is 2 and FE is square root of 2. So in total, the radius of the quarter circle, that is capital R, equals to 2 plus square root of 2. Okay, that is the reason that capital R equals to 2 plus square root of 2. But because of the fact that OFE is one straight line, according to rule 9, edge FE that is part of OFE must be also a straight line. So edge FE is a straight line that touches the circle, the small circle at points E and H. And any straight line that touches the circle at 2 points must be a chord. So edge FE is a chord, but edge FE is a chord that passes through point F, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge FE is the diameter of the circle. And we know that any diameter of any circle bisects the circle into 2 halves. That is to say, the diameter edge FE bisects the circle into 2 halves. This is the first half, it is a semicircle, and the second half is also a semicircle. That is to say, this is a semicircle. And for that reason, there are this shaded area, the value of this shaded area equals to the area of sector A or E minus the area of this semicircle minus the area of this orange shape. Repeat again, the value of the shaded area in total, it is equal to the area of sector A or E minus the area of the small semicircle minus the area of the orange shape HBO. We have already found out that the area of sector A or E equals to pi times 3 plus 2 times square root of 2 over 4. Now, in the next step, we have to find out the value of the area of this small semicircle. The area of any semicircle equals to the area of the circle that is pi r square over 2. R is the area of the small circle that is equals to the square root of 2 units according to what is given as the question. If r equals to the square root of 2 units, it means that r square equals to the square root of 2 squared, that is 2. So r square is 2 divided by 2. 2 over 2 is 1. So we have found out that in total, in conclusion, the area of the small semicircle equals to pi square units. The area of the semicircle equals to pi square units. The area of this small semicircle equals to pi square units. Now the only thing that is left to find in order to find out the value of this shaded area is the area of this orange shape. The area of the orange shape must be equal to the area of triangle FBO minus the area of sector, the small sector FBH. the area of triangle FBO minus the area of this small sector FB edge of the small circle must be equal to the area of this orange shape. Repeat again, the area of the orange shape B edge O must be equal to the area of triangle BFO minus the area of the small sector BF edge of the small circle. So what is the area of triangle BFO? The area of triangle BFO equals to the area of any triangle equals to the base of the triangle times the height to the base over 2. The base is square root of 2 and the height is also square root of 2 because it is an isosceles triangle. It is a right triangle. It is also an isosceles triangle. Therefore, the two sides are equal to each other. So the height, the base equals to the height. They are both equal to the square root of 2. So it is square root of 2 times square root of 2 over 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So we found out that the area of this triangle BFO is 1 square units. And we have to find out now the area of the small sector BFH. What is the area of the small sector BFH? The area of any sector is the area of the circle, the small circle that is pi r squared, times the angle between the legs of the sector that is 45 degrees over 360 degrees. R is the radius of the small circle. That is equals to the square root of 2. If r squared equals to the square root of 2, it means that r squared equals to the square root of 2 squared, that is 2. So pi r squared is 2 pi, and 45 degrees over 360 degrees, it is 1 over 8. So it is 2 pi over 8. Here we divided both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, found out that the area of the small sector B edge F is equal to pi over 4 square units. Therefore, in total, the area of the orange shape BHO equals to the area of triangle BFO. That is actually 1 minus the area of the small sector BFH, that is pi over 4 square units. So in total, the area of the orange shape BHO equals to 1 minus pi over 4 square units. And the area, the value of the shaded area in total equals to the area of sector AOE, that is pi times 3 plus 2 times square root of 2 over 4 minus the area of the small semicircle, that is pi square units, minus the area of the small orange shape, that is 1 minus pi over 4 square units. So the value of the shaded area equals to the area of sector AOE, that is pi times 3 plus 2 times square root of 2 over 4 minus the area of the small semicircle, that is pi. Here we open the brackets and we have here minus 1, and minus times minus is plus, so it is minus 1 plus pi over 4. So here we open the brackets here, and pi times 3 is 3 pi plus 2 times square root of 2 times pi, and here we have minus pi plus pi over 4 is minus 3/4 pi minus 1. Here we multiplied minus 1 by 4 and then we divided by 4 in order to become factor with the other two expressions that have the denominator of 4. We found out that 3 pi plus 2 times square root of 2 minus 3 pi minus 4 over 4. This is the value of the shaded area. 3 pi minus 3 pi is 0. So we cancel those two expressions. We left only with 2 times square root of 2 times pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2 and found out that 2 times square root of 2 times pi over 2 is square root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator 4 also by 2. 4 over 2 is 2. So in conclusion, found out that the value of this shaded area equals to either the square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. Okay? Thank you very much.